Okay, in part 2 of our exponential functions lesson, we're going to start with some modeling. So our first example says a lab technician begins with 3 bacteria in a petri dish. Every hour, the number of bacteria doubles. Write a function representing a situation where x is the number of hours and y is the number of bacteria to find out how long it will take for the dish to contain more than 100 bacteria. All right, so it's already telling us right here that x is going to represent the number of hours and y is going to represent the number of bacteria. It also tells us that it begins with 3 bacteria. So remember, when we're writing an exponential function, there's 2 things we need to know. We need to know what is the initial value and what is the multiplier. So when it begins with 3 bacteria, that gives us our initial value. It also then says every hour the number of bacteria doubles. So we know that the multiplier in this case would be 2. So we'll put this function together and we get y is equal to 3 times 2 raised to the x. Okay, so to answer the next part, we want to know when it will contain more than 100 bacteria. So we can use technology to do this. You can use Desmos or your graphing calculator. What we will do is in y1, we would put in our function, which is 3 times 2 raised to the x. And then in y2, we're going to put 100. And we can find the intersection of those 2 graphs. One will be the exponential function and one will be a horizontal line. We can also use our best friend, which is the table. We put these functions into our y equals and we go to the table. We can see that at 5 hours, the function would have 96 bacteria, and then at 6 hours, it would have 192 bacteria. So obviously, somewhere a little bit more than 5 hours is how long it would take to get to at least 100 bacteria. That helps us so we know how to fix our window. So I know when I'm setting up a window now, and I'm going to real quickly just fix this, guys. I'm going to go to a standard window. So I'm going to hit Zoom 6, which will be Zoom standard. That way my window is not messed up. So now I'm going to go back to the window. I know that my X max is going to show me, since I know the answer is between 5 and 6, but we're going to want to make our Y max bigger than 100. So maybe I might make it like 150 or something like that. You don't have to change your Y scale, but for me, I like to change it so it's not so thick on there, not trying to put a tick mark at 160 units. So then we're going to graph it. We're going to see that exponential function. We're going to see that line Y equals 100. And we want to find the intersection. So remember to do this, you're going to hit second trace, which is calculate. You're going to go to number 5, intersect. You're going to scroll over by the intersection. In this case, it wouldn't matter because there's only one, but we know sometimes there's more than one. And then you're going to press enter, and it's going to skip to the other curve, enter, and then just don't worry about guess. Just press enter again. And it gives us that intersection is 5.058. I know that using Desmos for these types of problems may be a little quicker, not as many steps, but remember that you're not going to be able to use Desmos going into the ACT or the SAT and most of your college or AP courses. So it's really good to understand and be able to program your graphing calculator. All right, let's look at the next one. A scientist has 100 grams of a radioactive substance. Half of it decays every hour. Write an equation that represents the situation. Sorry, this should be question A right here. All right, so we have our initial value because it says it starts with 100 grams of a radioactive substance. And it also says half of it decays every hour. So we know our multiplier is 1/2. So our function in this case would be f of x equals 100 times 1/2 to the x. Remember, you always put your initial value and then the multiplier is what's being raised to the x. In this case, it didn't define what x and y are, or x and f of x. So I think it's important to do that. So I'd just come over to the side and say where x is equal to hours and f of x is equal to the grams of the radioactive substance. So then it goes on to say how long will it take for 25 grams to be left? In this case, it actually comes out really nicely, because if you have 100 once, it's at 50, and if you have 100 twice, it's at 25. You can put this function right in your graphing calculator. Before I even type 25 in, I'm just going to go ahead and just type in the function and go to our best friend, the table. And you can see that at 2, we are at 25, so it comes out perfectly. If it doesn't come out perfectly, you're going to need to use a graphical representation so that you can find that intersection. So the next problem, a population of certain animal is being researched by environmentalists and has been decreasing substantially. Biologists tracking the species have determined the following data set to represent the remaining animals. Assuming the population continues at the same rate, what function would represent the population f of x in year x, assuming x is the number of years after or since 2010? All right, well, guys, if we look at our years, they are increasing by 1 each year, which is what we want to see. And when we look at our population, it is decreasing. But we have to figure out, what's that multiplier? What would we have multiplied 40,000 by to get 30,000? And then 30,000 by to get 22,500? Sometimes if you don't see the multiplier, all you have to do is take one of the numbers and divide it by the previous number. So what I mean by that is, if I take 30,000 and I divide it by 40,000, I would get 3/4. And then check to see if that works. And if you check, once you realize that from those first two, 30,000 divided by 40,000 is 3/4. If you then go in your calculator, 3/4 of 30,000 is 22,500. 3/4 of 22,500 is 16,875, and so on and so on. So just make sure that that multiplier works. All right, so our final function would be f of x is equal to 40,000 times 3/4 x. Now this is one that worked out very nicely, but sometimes we collect data that is exponential, but it's, a regression model. We know in the real world, not every point or every data value falls perfectly on this curve. So let's remind ourselves how we could use our graphing calculators to also find this function using our stat feature. I know it may have been a while for you since you've done a stat thing in your calculator, but it's a great feature. So we just come right here over by your arrows, and we're going to hit stat. And right under edit, we're going to go into edit. If you have data in your list, remember you just click up on the L1 or L2, and you're going to press clear enter. Make sure you do not delete the list. If you delete the list, then you have to get it back, which we can, but it's just extra steps. So clear enter. In the first list, you're going to put your X data. In the second list, you're going to put your Y data. All right, notice I did not type the years in for list 1, because we've written this function where X is the number of years after the year 2010. So 2010 would be 0 years. 2011 would be 1 year, because it's 1 year after 2010. And that makes your function a lot prettier too. All right, once you put your data in your list, you're going to go back, you're going to hit stat. You're going to go over to calculate at the top, and then you're going to go down. You may remember from Math 1, you did a lot of linear regression. Maybe in Math 2, hopefully you did some quadratic regression. I know in my Math 1 class we do quadratic regressions. And we'll learn some of these other ones, but what we want to go down to is 0, which is exponential regression. With my Math 1 students, we do exponential regression, but if you took Math 1 in 8th grade, I'm not sure, depending on what teacher you had, if you got to this. So we just press enter. It's going to give us our X list as list 1, our Y list as list 2. If we wanted to, we could store the regression equation. I'm not going to worry about that for right now, but I'm just going to go to calculate. It's going to give us our basic formula, y equals a times b raised to the x, and then it gives us our a value and our b value. It's a tad bit off because as you keep multiplying by 3/4, those numbers at the end are rounded a little bit because of the population. But technically, the initial value is 40,000, and you can see that 0.749999 is practically 0.75, which is the same thing as 3/4. I highly recommend you practice doing this. You're going to want to remember these steps in the future for other regression models. Okay, so what about percent growth and decay? Exponential growth and decay with a constant percent increase or decrease over specific time periods can be modeled using the following functions. Guys, these are derived from the function y equals a times b to the x. The only difference is to get your base or your multiplier. If it's a growth, you're going to do 1 plus r. If it's a decay, you're going to do 1 minus r. All right, so what we mean by that when we say that, r represents the decimal value for the percent. So if something's like increasing by 5%, we'd have to change it to a decimal and make it 0.05. So let's make sure we note that over there, where r is the decimal value. In other words, you would do percent divided by 100 to get that r. All right, for growth, the base is 1 plus r. We have to have the 1 there because the 1 holds what you had, and then you add that rate to it so that it adds that percent. When it's for decay, the base is 1 minus r. Because remember, the multiplier is always what you keep. So if you have something decaying by 20%, you're really keeping 80%. So that's why you would say 1 minus 0.20 so that the multiplier was 0.80. All right, so let's look at some problems. By the way, you definitely need to learn these formulas. They are extremely important, and they are not given to you on assessments. We did these back in Math 1 too. You just have to learn that anytime it grows or decays by a percent, you do that 1 plus r or 1 minus r to get your base. Teen spending is expected to grow 3.5% annually from $79.7 billion in 2006. Write an equation and draw a graph to show the spending growth since 2006. Okay, as soon as you see any word problem and it starts talking about something growing or decaying by a percent, immediately you should know that this is going to be an exponential function. In this case, because it's growing, we know that we'll be using that growth formula. So let's write out what we know so far. We know that the initial value, which is the same thing as A, is equal to 79.7 billion. Please do not put all those zeros in there. We're just going to know our answers in billions. All right, to get our R, you have to take the percent and change it to a decimal. Now, most of us at this time, we know we just moved that 2 places to the left. But in case you're one of those people who mess that up, it's just that percent out of 100, which would be 0.035. And then we know that the year 2006 represents t equals 0. All right, so let's set this up. If we were to write this function, we would say f of t is equal to our initial value, 79.7 billion, times 1 plus r. And I'm going to write it out for this one. Most of the time, I'll just go ahead and put it together. Because really what you're doing is you're saying 100% plus 3.5%, because you keep 100% of what you had. You add 3.5%. That becomes 103.5%. And then when you move that decimal 2 places to the left to get your multiplier, it ultimately gives you that base, or that multiplier, is going to be 1.035. And of course, we raise it to the t. T is the same thing as x. T is just representing time in this case. So when I put this together, our function is f of t equals 79.7 times 1.035 raised to the t. Remember, anytime we have an exponential function that grows, the base has to be a number greater than 1. If you don't have that 1 there, you just have 0.035, this is not going to grow. It is just going to decay. And I'm going to go ahead and define my variables. So I'm going to say where t is the number of years since 2006, and f of t is in billions of dollars. All right. I know it's been a while since you've done this, but you did do these problems in Math 1. So why don't you go ahead and try the next one. You're just going to write a function, see if you can set it up. And then for number 6, go ahead and see if you can just write the function. I know number 6 has 2 parts to it, but see if you can write the function. Pause the video, and when you're finished, start the video back. All right, so in number 5, that initial value is 68 milligrams of caffeine. The key word here is that it's being eliminated. So we know this is a decay problem at 12.5%. So if you use your formula, your A is 68, your R is 0.125, pop it into the decay formula, which is 1 minus R. Remember, if it's decaying or decreasing, it's 1 minus R. If it's growing or increasing, it's 1 plus R. Or another way to think about it, which is kind of what I do, if you're losing 12.5%, you're keeping 87.5%. So therefore, the multiplier is 0.875. You just change that percent to a decimal, and then you kind of don't even really have to use that formula. And then there's our function. All right, so we know that in the beginning of 2008, we have 6.7 billion people, and it is growing at a rate of 1.16% each year. So this is a growth problem. We set it up. We should get the function f of t is equal to 6.7 times 1.0116 raised to the t. Then we have to do the next part. In what year will the population be double? In order to answer that, we're going to use our technology. So we know that this function is growing exponentially. And so I'm just going to do a little sketch here. It's not going to be perfect or beautiful, but I know if I was to graph this, it would look something like this. It's going to grow exponentially. I also know that if I double 6.7 billion, that's 13.4 billion. And I've just got my y-axis here representing billions. I'm not going to put all those zeros on there. So what I need to do is I need to graph those two functions and figure out where is that intersection so I know how long it's going to take to double. And to do that, we're going to use our graphing calculator. Of course, you can always use Desmos too. Start out my graphing calculator by putting the original function 6.7 times 1.0116 raised to the x. And then I'm going to come over here to my best friend. I'm going to say, okay, well, if I sit here and I scroll down this table, I'm trying to get to 13.4. And I can see that at 60, it's 13.385, but at 61, it's 13.54. So technically, I could answer this question just by looking at my table because it says in what year. But if we do this graphically, what we want to do is go back to y equals, come into the y sub 2, type in 13.4, and then we're going to have to set up our window. Obviously, we need our x max to be bigger if we know it's around 61. So maybe I might make my x max go to 70. And then if I do that, I'm going to make my x scale 10. Now my y max does not need to go all the way to 150. That would be way too big. So I'm going to make it go to, if we're trying to get to 13.4, I might go to, I don't know, 15 or 20. And I probably don't need my y scale to be that big. It can just be 1. All right, so then we hit graph. We should see that exponential function and that horizontal constant function on there. So then we're going to go to second trace, which is calculate. We're going to go to intersect, and we're going to scroll over by that intersection. And once we get close to it, we might not be able to get right on top of it, but as close as we can. When it says first curve, press enter. Second curve, press enter. Guess, just press enter. And it'll show you that it's about at 60.099. Okay, so since this was the year 2008, to answer this part of the question, what we're going to need to do is we're going to have to take 2008, add a 60.1 to it, which brings us to 2068.1. But we know if it's 0.1, it's still within that year. So to be able to answer this question, we would say sometime in the year 2068. Now, of course, we know that's only if it was to continue at that constant percent rate, which the reality of that's probably not correct. All right, last problem. In 1983, there were 102,000 farms in Minnesota. But by 1998, this number had dropped to 80,000. Write an exponential function that models this problem. Let x represent the number of years since 1983. Okay, so what we need to do here is create points. What we know from the information given is that in 1983, there were 102,000 farms. But then by 1998, there were 80,000 farms. And since it says to let x represent the number of years since 1993, we're going to change that to the year 0. And since 1998 is 15 years after 1993, we'll let this be 15. So I'm going to set this up in a little table. So when x is 0, we have 102,000. And when x is 15, we have 80,000. Well, remember, in order to write an exponential function, we always need to know what the initial value is. Now that we've changed 1983 to be 0, that gives us that initial value. We know that this number right here represents our a. So using our formula, y equals a times b to the x, we're going to substitute that in for a. All right, the problem is we don't know the multiplier in this case. So we need to figure out what that multiplier is. But what we do know is another point on here. So what we're going to do is we're going to substitute this point 1580,000 in for x and y in our formula so that we can solve for that base, for that multiplier. So for x, I'm going to put 15. For y, we will put 80,000. All right, and then we're going to work this out. So the first step in solving this exponential equation is to isolate the base. We've got to get that base by itself. So to do that, we're going to divide each side by 102,000. All right, so if you stick that in your calculators, that should give you approximately 0.784. And then we just have left is equal to b to the 15th. All right, so we want to solve for the base, so we have to undo that raised to the 15th power. To do that, you either have to take the 15th root of each side, or what I find to be easier is raise each side to the 1/15th. Last year, you should have learned with your exponent rules about fractional exponents, and fractional exponents are the same thing as radicals, and I find that's just easier to type in my calculator. So if you go in your calculator and you put your 0.784 in and you raise it to the 1/15th, it should give you the base. And so that gives us approximately 0.984. All right, so we're now going to put this together to be able to write this function, and we would say y is equal to 102,000 times 0.984 raised to the x. Okay, suppose the number of farms in Minnesota continues to decline at the same rate. Estimate the number of farms in the year 2010. Okay, so the first thing we have to do is figure out how many years have elapsed. If we want to know for the year 2010, and this started in 1983, we would find the difference of those, which is 27 years. Then using our formula that we just came up with, this function right here, we're now going to substitute that 27 in for x. So y equals 102,000 times 0.984 raised to the 27. And you can just pop that right in your calculator. And if you do, you should get that that is approximately 65,988 farms. Notice in this case I do round to a whole number because we're not going to have part of a farm. And that's our final answer. And in class tomorrow, we will work on the practice.